Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the today's session on Green's Theorem, Part 2. In the last session, I have introduced the Green's Theorem, the statement of Green's Theorem, and we have verified Green's Theorem for the given problem. So, verification has been done. Now today, I am going to continue the same concept and discuss some applications. That means when we can apply this Green's Theorem. Green's Theorem can be applied if the line integral is in the form mdx plus ndy. Then we transform it into a surface integral by finding dou n by dou x minus dou m by dou y. So we evaluate this surface integral. Now the Green's Theorem states that line integral mdx plus ndy is equal to the surface integral dou n by dou x minus dou m by dou y dx dy, which was discussed in the last session. Now, as an application, let us solve this problem. Evaluate by Green's Theorem the line integral where C is the triangle enclosed by the lines y equal to 0, x equal to pi by 2 and pi y equal to 2x. Now the solution. So given line integral m dx plus n dy is equal to the line integral y minus sin x dx plus cos x dy. So that implies we can identify that these two are the functions m and n. So m is the function y minus sin x and n is cos x. To apply Green's Theorem, we transform this into surface integral, and to evaluate that surface integral we need to calculate dou n by dou x and dou m by dou y, these two values. So m with respect to y partially. So the derivative of y is 1 and here for this 0. Dou n by dou x is minus sin x. That implies dou n by dou x minus dou m by dou y is equal to minus of sin x plus 1. So, since the surface integral is having the function dou n by dou x minus dou m by dou y, so first we calculate that dou n by dou x minus dou m by dou y. So, minus sign common, so sin x plus 1 is the function. Now, by Green's Theorem, the line integral m dx plus n dy is equal to surface integral dou n by dou x minus dou m by dou y dx dy. That is equal to surface integral just now we have calculated with minus sin x plus 1 dy dx. So minus of sin x plus 1 first with respect to y, then with respect to x. And now we need to find the limits of y and x. Now for that, let us consider the curve. The curve is a closed curve which is a triangle bounded by the lines y equal to 0. So, to draw that, y equal to 0 means x-axis, y equal to 0 line, then x equal to pi by 2, a line parallel to y-axis, x equal to pi by 2. So, this is the line x equal to pi by 2 and pi y equal to 2x. So, y equal to 0, x equal to pi by 2 and pi y equal to 2x. So, y equal to 2 by pi x, and that will be a straight line which is in the form of y equal to mx, a straight line passing through origin. So, this is the line y equal to 2 by pi into x. Now, let us denote the points O, A, B. So, this is the point origin and here this is the value of x is pi by 2 here. So, pi by 2 comma 0 and here the point of intersection of these two, x equal to pi by 2. If you substitute here x equal to pi by 2, put x equal to pi by 2. So, you will get pi by 2 comma y value is 1, pi by 2 comma 1. Now, we need to find the limits of y in terms of x and then x in terms of constants. And we know that the values of y changes vertically. So let us draw a vertical strip or a line. Then y changes from bottom curve to top curve. So y varies from 0 to 2 by pi x, and x varies from, now we need to find x constants, x limits as constants. Here x equal to 0, here x equal to pi by 2. So therefore, this line integral m dx plus n dy is equal to minus of x from, here x from 0 to pi by 2. So x from 0 to pi by 2, y from 0 to 2 pi by 2x by pi sin x plus 1 dy first, then dx. So we need to integrate this. So that is equal to minus, so that is equal to minus integral x from 0 to pi by 2. Now with respect to y, so sin x plus 1 is constant, y from 0 to 2x by pi, 2x by pi. Now let us substitute that, 0 to pi by 2, sin x plus 1 by applying the upper limit 2x by pi dx. So here 2 by pi is constant, so minus 2 by pi, x from 0 to pi by 2, we can multiply this, sin x into x, so x sin x plus x dx. Now we need to integrate this with respect to x, x from 0 to pi by 2, so x sin x plus x from 0 to pi by 2 x dx. So that's equal to, so that is equal to minus 2 by pi into, here we need to apply integral by parts, x into sin x. So first function, integral of second is minus cos, minus derivative of first function is 1, and again integration of this result, so minus sin x, and then here plus x square by 2 from 0 to pi by 2. So this is equal to minus 2 by pi into upper limit, so minus pi by 2 cos pi by 2 plus sin pi by 2 plus pi square by 4 into 2, 8, and lower limit here 0, and again here sin 0, 0, 0. So this is minus 2 by pi into, so we know that cos 90 is 0, so this becomes 0, sin 90 is 1 plus pi square by 8. So this is equal to minus 2 by pi minus pi by 4. So minus 2 by pi plus pi by 4. Hence, the line integral can be evaluated using Green's theorem by transforming into a surface integral. Similarly, let us solve one more problem. Evaluate by Green's theorem. So the given integrand is in the form of m dx plus n dy, where C is the rectangle with vertices. So here, solution, given integral C m dx plus n dy is equal to integral C x square minus cos hy dx plus y plus sin x dy. So therefore m is x square minus cos hy and n is y plus sin x. Now let us calculate dou m by dou y, which is with respect to y, so we treat x as constant, and the derivative of cos hy is sin hy, so minus sin hy. Then dou n by dou x, we treat y as constant, so 0 here, cos x here. That implies dou n by dou x minus dou m by dou y is cos x plus sin hy. Why we are calculating all this? To apply Green's theorem, we transform this line integral into surface, and in surface integral the integrand is dou n by dou x minus dou m by dou y. That's why we are calculating all this. Now what is the, by Green's theorem, line integral m dx plus n dy is equal to surface integral dou n by dou x minus dou m by dou y dx dy, which is equal to, now what is dou n by dou x minus dou m by dou y? Cos x plus sin hy. Cos x plus sin hy dx dy. Now to find the limits of x and y, let us draw the given curve. What is the given curve? It's a rectangle with vertices 0, 0. So the origin. Next, pi comma 0. So I can consider some point here. Origin A, pi comma 0. Then pi comma 1 and 0 comma 1. So this is pi comma 1, the point C. And so OA, this is the point B, and C 0 comma 1. So the curve is bounded by these four lines OA, AB, BC, CO. Now for example, if we evaluate the line integral, we need to evaluate along each line from O to A, then A to B, then B to C, and then C to O. But instead of finding line integral, if we transform it into surface integral, it is easy to evaluate the double integral. So because we can evaluate the limits directly. Here I can say x changes from, here what is the value of x? 0. Here pi, 0 to pi. And y changes from 0 to 1. The value of y is 0 and maximum it reaches 1. So direct limits, we can obtain direct limits so that we can evaluate the double integral in an easy way. So x from 0 to pi, y from 0 to 1, integral cos x plus sin hy, first with respect to y, then with respect to x. Now let us integrate with respect to y first. And here cos x, we can treat it as constant. So cos x into integral dy is y, plus the integration of sin hy is cos hy from 0 to 1 dx. So this is equal to x from 0 to pi. The upper limit, we need to substitute the limit in place of y. So this is cos x into 1 plus cos h1 minus y. In place of y, we need to substitute 0. So 0 minus cos h0. So this is integral from 0 to pi cos x plus cos h1 minus 1. Cos 0 is 1. So the last integration is with respect to x 0 to pi cos x plus cos h1 minus 1 dx. So now integration with respect to x. Integral of cos x is sin x plus cos h1 minus 1 is constant into x. So whole from x equal to 0 to pi. So apply the limits, sin pi plus pi into cos h1 minus 1 minus sin 0 minus 0. Sin pi is 0. Since sin n pi is 0 where n is an integer. So plus pi into cos h1 minus 1 minus sin 0 is 0. So the final answer is pi into cos h1 minus 1. So instead of evaluating the line integral, we transform it into surface integral, and then by evaluating the double integral, it is very easy to obtain the actual answer. This is the best example because here for this problem, if we want to evaluate line integral, along each line we need to calculate. So along OA, that is first line integral, then along AB, second, then along BC, then along CO. So the line integral is sum of these four line integrals. So it takes much time. Instead of evaluating line integral, if we transform it to surface integral using Green's theorem and obtain the limits, it is very easy to evaluate this double integral. So in today's session, we have solved some problems on Green's theorem as applications. By applying Green's theorem, we can evaluate the given line integral. Simply, we transform the line integral into surface integral. So line into surface using Green's theorem. So in the next session, I am going to introduce the third theorem, Stokes' theorem. In vector integral theorems, we have three theorems: Gauss divergence theorem, Green's theorem, and Stokes' theorem. Already Gauss divergence and Green's theorem and the problems were finished. Now in the next session, I am going to start Stokes' theorem and problems on Stokes' theorem. Thank you.